Okay, funny part. Funny part. So I shouldn't remove it, but since I did it, I will write Fock solution again. Okay, so what I want to show that eta less than tau square U in plus U squared, U scattered is approximately 0. Okay, for AI, we know the asymptotics. For CI, so write these results again. So for Z bigger than 0, CI grows SBI. And precisely and kind of what I'm doing here, it's a practical guide. So you can, these bits I'm writing here, I'm writing them without any explanation because these are bits from Wikipedia or standard textbook. So that's how you can approach similar problems. You find asymptotics from some reference guide. So it grows exponentially. And that's important because if it grows exponentially, we have a potential of, we potentially can have problems with convergence. So we should check whether our y integral converges. So it might diverge. Of course it's not. It's a good integral. But we don't know it yet. And for negative, it behaves as an outgoing wave, because that's the way we designed this function. That's how we came up with this function. We wanted to behave an infinite wave. Okay, so we should study this combination. Probably from this asymptotic, it's clear then Ci over Ci is small. Positive psi and eta. So if it's all positive, then we have either decay coming from this bit, or we have growth here, but this growth cancels by this faster decay, if it makes sense for you. So this thing grows exponentially. And if they are both positive and psi is bigger than eta, the order of growth is smaller here. So the whole combination decays. Otherwise, this thing oscillates, but this thing decays exponentially. So we probably should not worry about positive size. So we can restrict this integral only to this bit. And I'm not worried about AI because it exponentially decays for positive xi. So all contributions for positive xi's, they are exponentially decaying. They will not give us any saddle points. This is the first bit of analysis. Then I will do a bit of algebra. So what I do next? I take asymptotic expression for this thing, and for this thing. So I have this asymptotic and asymptotic for AI. And then I just plug in all of them, and I have some saddle point type of integral. I will write it down, and it should look believable for you. I suppose you won't be able to follow. But there is like a bit of algebra, but I decided to skip it. So, and I have two terms because I have two exponents coming from AI function. Probably I shouldn't call it AI, it's a term that has no bad connotations. Okay, do you recognize this? My integrand. This integrand. We had the same integrand for plane wave. So this integral is the same as we had for plane wave. It just differs by sign and upper limit of integration. But for saddle point method, upper limit doesn't matter. And sign gives us minus. So this term gives us approximately minus 2m, which cancels the plane wave. You can probably ask at which point we use the fact that tau square is bigger than eta, but we haven't used it yet. We will use it for estimation of the second part of the term. So I will show that second term doesn't give any saddle point contributions. That's when I will use it. But this part is clear. So second term, it is slightly different. Okay, let's do some second grade algebra and show that derivative of this thing does not have any real solutions. So I will, for convenience, introduce variable which is minus xi because I have minus xi here, here, and then my zeta is bigger than 0 because my integration happens from minus infinity to 0, so this variable is always positive. And my phase function is this. So what I need to show that this equation does not have any positive roots. So how we do it? Let's write it. And of course we can build, so this thing we can build unusual, I think it's called Cauchy inequality, because it's simpler than this. So for positive zeta and eta, this is true. Because we kind of do, no. If we had square here that would have been, we just would have taken a square product and we would have had two additional terms and we subtracted them, then this thing should be definitely smaller. It would have been bigger for square, but smaller for cube. And okay. What else? But now we have our condition. Our condition that tau is bigger than delta 1 over 4. This is the fact that we have our point of observation in shadow zone. So then it means that this thing is smaller than plus tau. So we compare these two terms. So and I have an O inequality like this. So I have no solutions. And this is the point where I use that I am in the shadow zone. Otherwise, I would have had some solutions, And the second term, as you might guess, it would have generated the reflected field. Move fast. So this is the first part of the analysis I wanted to do today. The second bit is slightly more involved.
Sorry, why did you multiply whatever the variable is called by 2 in the second part of the equation?
Yeah.
Well, okay, you have the Cauchy inequality, then you use this condition tau, but then
I compare it with this thing. So this thing, it's a good point.
it's just if it's less than.
Yeah. Let's.
Well, I guess it's called anyway.
Yeah, it holds anyway, but now I can figure out why.
If it's less than the same expression but without 2.
Yeah,
Then
it's
it's
fine.
false.
We just add it so it's bigger. So I have a stronger one. Yeah, I have a stronger. So this is like a weaker one. I can give it like this. Okay, the second bit I want to do is to show that this integral has so-called fitting waves. But before we move to this simple, I need to introduce some additional properties of Airy function, like Airy functions. And reminding the equation, so this is Airy equation, and first thing I want to stress is if Vz is a solution, then this thing is also a solution. It can be checked directly. So this equation has a rotation symmetry. 2 pi over 3. You can, this thing can be easily checked. And also, I will use this fact. I won't be easy, but from this fact you can show that Ci can be expressed like this in terms of Airy function. This I won't be proving today, but one way you can to see it is to write down the asymptotic for this function and write down the asymptotic for this function. And these two asymptotics, they will coincide. And then you can then make it more formal, because you can study a solution in the vicinity of the singular point of this equation. In the vicinity of the singular point of this equation, you have only two independent solutions because it's an equation of the second order. So it follows from general theory of ordinary differential solutions. And then any solution can be obtained as a combination. And if you were able to match your solutions asymptotically, they are matching exactly. But for this general theory, of course, you need to do a lot more work. And I refer you to the book by Frank Holger. Asymptotics expression facts. I think his son is now professor in UCL. I think he's from London. I don't remember which university he was, but this is a very good book if you want to know more about special functions and theory of ordinary differential equations. That's a very well written book, but of course it's not simple. It's far from simple. So one point, and yeah, like this what we should know also about this equation. This equation only has one singular point, which is infinity, because it's a singularities of the coefficients. Coefficient has growth at infinity, and yeah, or it leads to a regular singular point of order 2, whatever it means. But the good thing that follows from it, that we actually don't have any branching for the solution. So the solution area function does not branch anywhere. It's analytic everywhere. It's like meromorphic everywhere, and it has poles. And my aim is to find poles of this function, and then once I know poles of this function, I can deform my contour of integration. Now it will be back to infinity. And study polar contributions. So I need to find poles of this function, because this thing is like zeros of this function. This thing is in the denominator. So, and if you open Frank Holger, it will say that I will write this asymptotic. It's a bunch of different asymptotics I write for you today. Maybe you already heard, but there is like a very general way to write an asymptotic for area function. So what does it mean? What does it mean? So it means we can use this asymptotic almost on the whole complex plane. We used it so far only on negative, on positive real axis. it kind of says that we subtract some region in the vicinity of 0, and then almost so here we are able to use our asymptotic. And that's probably how also you should interpret Wikipedia. If you read Wikipedia, it usually says for each arc the asymptotic is valid. This is arc. Cool. So from this asymptotic, and what we use here, we actually use a combination of both asymptotics from here and from here, and that's when we get a sign. So we had sign of something. We get a sign, and it means we will have zeros of this sign. Let me draw you the behavior of the function. So this is the argument of the function, this is values of the function. And behaves like this. It has so-called Stokes line. It has area of exponential decay. So we knew that area function exponentially decays on real axis for positive arguments. I say it can be extended to this domain. And here our function oscillates, here, and here. And here we have exponential growth. And what else should I put? Yeah, of course, since we have a symmetry, 2 pi over 3, this angle should be pi over 3. Then we can rotate this picture to pi over 3. And the most important bit, we will have zeros here. And approximate location of the zeros comes from asymptotic. So this asymptotic is sum of these two, which will give sign, and sinus will turn to 0. Of course, if we want to be formal, we also need to study our function for small z, but for small z we can build it as also asymptotic solution. We can build a series and we can check whether we have any other zeros. And once we do this to asymptotical status, we can conclude that's the only zeros we got. And what else? Okay, let me write from the previous asymptotic expansion, approximate location of zeros. So, what this was all about? This was to find the zeros of this function. And for this function, I just rotate this picture here by 2 pi over 3. And if I rotate it, this thing, okay, let me do it. So I give the rotation. And now these 3 lines, of course, they stay at the same place. But after rotations, all my zeros moved here. That's probably what it's all about. And yeah, if you wanted to make this thing more formal, you go to over. And finally, we can move to the final bit of our lecture. I hope I will be able to communicate in 12 minutes. This is triple waves.
So what were you rotating it by? I don't think I heard. Was it pi over 4 or 3 pi? So when you were rotating it, you said by some value of pi.
2 pi I over 3.
Thank you.
Pi over 3. Triple waves. So, what is the result? You know this function has zeros and the whole y integrand has poles. Let's deform our control integration, compute these polar contributions, and then just try to analyze them from a physical point of view. Because they might be important. Like any pole usually in wave theory corresponds to some propagated wave. So it's worth studying. Okay. So we have our function, we have our poles, and they are going to infinity, so it's infinite amount of poles. Original contour of integration here. Let's deform it like this. So when we deform it like this, using the Cauchy theorem, we should subtract all contributions. Okay, of course, when we do it, this deformation should be somehow motivated. So if when we do these things on practice, we should to check that the integral along this line is smaller than the integral along this line. Otherwise, it doesn't make much sense. And you can do it, yeah, it's fine. You can check it. I should also put the axes. This is the left side, this is inner side. And using the residue theorem, I can just write down the contributions coming from a polar term. Let's denote one of these poles as lambda, as this complex number as lambda, and a pole contribution corresponding to this lambda like this. Should be clear for you how to obtain this result, is it? So we applied no residue theorem, this thing we expanded into Taylor series, and this is just a first order pole contribution. And that's why we have here Ci prime, which is the first derivative of Ci, and this is like all the other terms is what's left. Okay?
How can you define quantum like this? Just above this.
I mean, I started from here and I just moved.
Yeah, but isn't there a growth region above the?
No.
No?
No. You know, but that's a good question. You need to check. I mean, anyway you can do it, but that's what I said. If your function grows in this area, it doesn't make sense. But you can do it, and like as far as your deformation is finite, it doesn't matter. But here you need to compute all these three things and check whether they exponentially decaying or not, like I did before. And they are, because we discarded the part from positive infinity, so we were estimating this integral before from minus infinity to 0, and this is thing lies in the positive area. But of course you need to do this. You can check it by stating the asymptotic of this combination.
Ah yes, so it's only the area function.
Yeah, you need to, like, area function
I was thinking about the picture.
exponentially. Area function decaying exponentially. Until, here area function start to grow, but you also have this term and this term, so you need to carefully start. So this is our, and this thing you obtain using residue theorem. It's fine.
I can check that simple terms.
You expand?
Yes.
How do you you check whether you have the first derivative? I mean, I just showed that my function is analytic. Basically, you do the same thing. You have an asymptotic formula which is sine. For sine, it's simple poles. And then you need to carefully prove that you don't have anything else. So it's not a trivial result. But like, if we consider ourselves as a plate people, we take the first asymptotic term and we believe that's what we have on the field. And if we want to be more careful, we go to over, and then we study our asymptotics everywhere. So we need to establish our asymptotics in all regions, and then we can say. But there is no other. Here I implied that I have a simple pole. It's not obvious. But that all comes from theory of special functions. Anyhow, so only this bit depends on variables t and eta, on our space variables. And let's rewrite this bit asymptotically. So this is some wait. It has a phase term, it has an oscillating phase, and what I will show that this bit of phase corresponds to creeping along the surface of cylinder. I'm not sure, we'll just draw a picture and then you will try to complete yourself. Ask me next time. And this bit corresponds to detaching from the surface of the cylinder and straight propagation to the point of acceleration. So let me draw a picture and maybe it will make things believable for you. So we have our cylinder. We have center somewhere. And this is 0 point. This is where we had our critical wave. Right. And what I'm claiming is this bit of propagation corresponds, gives the following phase shift. And then I should, and I have attaching point here, so let it be our point of observation, tau and eta. And this bit gives us this phase shift. So this bit should be believable because it's what we just get from plane wave. You can substitute and check. For this bit, it's like some simple geometry. Zero, and as it the next hint that so we have a tangent line here, so like or physically the thing is more or less makes sense. So we say our wave propagates along the surface, then at the point when we are finally able to see it, it detaches from the surface and propagates along the straight line. And then if I just generalize my equation of tangent line for arbitrary point, that's how it looks. Then I can say that this distance is approximately the square root of eta. And that's that. So if we moved to like tau, we would have got a phase shift E lambda tau. But since we moved just to here, so we have phase shift E lambda tau minus square of eta. That's how I justify and interpret this thing. You know, it's a bit wiggly because we have ugly coordinates which we are not used to, but I hope it looks believable enough for you. That's it. That's how we can interpret this contribution. And final bit I will say for today is that our field can be presented as sum of two components. And this thing is a series. of terms like this, of creeping waves. It's kinda, so we will have two terms, one corresponding to reflected waves, that's kind of like probably mainly reflected wave, and another corresponding to creeping waves. And it's kind of funny, we can take this deformation all the way up, and if we or in the result we can do this deformation. I'm not sure we actually can do it for plane wave problem, but we can do it for point source problem for sure. Then we can just have something like a model decomposition for our solution. And this thing is called Watson transform, when you can deform your integral to a sum. And that's what happens in some waveguide problems. So you kind of have array representation and a mode representation. It's two complementary representations of the field. Okay, I think we finished almost on time. Thank you for your attention. Like, subscribe, and press the bell. See you next time, I hope.